So we will wait for just a couple of minutes just to start the seminar. Okay, so for those of you who are there, just please wait for a couple of minutes and we will start the seminar.
I think I have to get out of the presentation to do that.
Okay, so I think we can start. Okay, so welcome all of you. So welcome to this DIPC seminar that today we'll have well, a slightly different format from the ones that we usually organize at DIPC. So we have today two speakers with us. So let me introduce to Antonio Duarte Postigo and Cristina Thöne. So both of them, they come from the Astrophysics Institute of Andalusia in Granada. Both of them, let's say, they work in explosive transients, galaxies, the study of galaxies, instrumentation. So Antonio, he made his PhD in Granada, in the same place in which they are working now, but he also had he was also working as a postdoctoral fellow in Italy, in Merate. He was also working in Copenhagen in the Niels Bohr Institute. Cristina herself, she made the PhD in Copenhagen in Denmark, in the Niels Bohr Institute too. She was also in Merate in Italy. Now she's in Granada. So both of them, they will be talking today in a combined seminar. So I'm really glad to have you, both of you, Antonio and Cristina, here at the IPC, and we are looking forward to your talk. So please feel free to start. Oh, so sorry, let me just remind all of you that at the very end we can have time for questions. So either you can ask, let's say, for your microphone to be unmute, or you can also send the questions to the chat, wherever you prefer. So again, so welcome, Antonio, Cristina, and feel free to start.
Okay, so good morning, everyone. We're going to give some double feature talk today featuring two people. Because we work in somewhat similar stuff, but each of us has its own specialities. And all the talk will be about, as was said, explosive transients. So we actually both come from the field of gamma ray bursts, but have since then extended our research to, well, anything that's exploding in the universe, because that's exciting. Okay, now this one doesn't switch. My slides don't want to move. I'm sorry. No, okay. So this is the research group that we have currently in Granada. So we are currently 6 people. There's someone who hopefully is going to finish her PhD at some point, but she just got a job as a data analyst. And below you see some people that we had before. Most of them have now very nice positions in other countries, in other institutes. As you see, we are a very international group. So, of course, naturally, there's some majority of Spanish people over time, but we also have people from several other mostly European nations, and we are very proud of being one of the most international groups at IAA. And the group got founded more or less. It was like a slow process until it really got going, like in 2012. From like 2015 on or so, we started to really grow and have more people and get funding. And so we have been able to attract quite some funding, and we have been also very successful in attracting personal fellowships. So most of our postdocs have actually been coming on personal fellowships like Juana Cierva or Ramón y Cajal. And we also managed to get quite some publications, and whenever we have time at GTC, we are actually the world record holders in that year or that semester in determining redshifts of gamma ray bursts. So if you give us time, you get a lot of redshifts. Okay, so now I'm going to talk a bit about the general overview of the things that I'm doing. So the stuff that we are doing is related to the life cycle of stars, focusing on the death of stars, of massive stars. So stars get formed in a molecular cloud in a star-forming region somewhere. Then stars, that the more massive they are, the shorter they live. So if they have, so a lot of the things that we deal with have masses of like at least 20 solar masses, or everything above 8 solar masses is likely going to explode in a supernova, but we usually deal with things that are much more heavy, and they only live a few million years. And so, as I said, some of them go supernovae, but you can also, some of them that have very extreme properties. So we think they have to have a very high rotation still retained, and a very high mass, and probably low metallicity, and then they can turn into a gamma ray burst. That's one way to make a gamma ray burst. There's a second way, which goes through two supernovae first, because you need two supernovae that produce two neutron stars. And at some point, these two neutron stars, if they are not too separate, they will merge. And in the merger, you produce something, you have very similar processes going on. You produce what we call a short gamma ray burst. So the actual gamma emission is much shorter in these mergers than when you have a collapse of a massive star where you have a lot of material falling in and accreting. But what you observe is actually rather similar, because both of them have, like, you have some very rapidly rotating thing, you can form some accretion disk, and you have very strong magnetic fields, and you form two highly relativistic jets. And since 2017, we also conclusively know that the short gamma ray bursts are connected to the merge of the neutron stars. That had been a theory that had been going on for 20, 30 years. For the long gamma ray bursts, we have been knowing for about 20 years, 25 years, since 97, that they are connected to the collapse of massive stars, because we have detected a supernova after the gamma ray burst related to that event. But for the short gamma ray burst, we had to wait for the first detection of gravitational waves from such a system. And since then, we know that that our model of two colliding neutron stars was correct. And of course, what's important in all these processes is all these processes are very important also for the evolution of the universe, for the chemical evolution of the universe, of galaxies, and ultimately us, because it's in those explosions that a lot of the elements that we are made of, Earth is made of, are created. And so if they wouldn't exist, and that's also a very hot topic ongoing, how much of this material is produced in which of these explosions, how many explosions do we need in order to get the material in galaxies and on Earth that we observe. Okay, how do we detect a gamma ray burst? So gamma rays, fortunately, do not penetrate the atmosphere very much. So if you want to detect a gamma ray burst, we have to go into space. So we have dedicated satellites out there that detect gamma ray bursts. So a gamma ray burst goes off, and the satellite says GRB, GRB, and of course transmits it down to Earth. That goes in real time. Then usually not a person, but a system is saying GRB, and distributes it to all the planet and everyone that's subscribed to such a system. And then we trigger a telescope, and then you usually have someone at the telescope, and because these gamma ray bursts have to be observed very quickly, because the gamma ray emissions you saw before, they're between 2 seconds and some can be several thousand seconds. But then the afterglow afterwards is also not going to be bright for very long. It can be a day, it can be several days if you're lucky, but usually you should be there within a day. And so you have to interrupt the observations of someone that's at the telescope. So there are dedicated programs that says you have the right to interrupt. But of course, sometimes you make someone upset. They say, like, you just had very good seeing, and no. So we are not always popular with the normal observers. Okay, so this is the processes that we have ongoing in the GRB jet. So we have some kind of central engine, which is a forming black hole either by a merger or by the collapse of a massive star. And so we have a highly relativistic jet coming out of this system, and you have highly relativistic shells of material that with very slightly different velocities or gamma factors in that case actually. And they create internal shocks, and those internal shocks produce the gamma rays that we observe in the gamma ray burst. And when the jet starts to slam into the circumstellar and intergalactic interstellar medium, you create the external shocks that create an afterglow that goes all the way from X-ray to radio wavelength that we can observe in anything that's available electromagnetically. You can also get reverse shocks that have some effect in the light curve that you can observe. And finally, there is whatever system you have. If you have a collapsing massive star, you have the supernova coming out on top of it, which we observe much later also because a supernova is actually, what you observe in optical light, for example, is much fainter for the supernova than the afterglow from the jet. And a supernova also takes a while to, let's say, build up. I mean, the star explodes, but what you see in a supernova is usually the decay of radioactive nickel, and that takes a while. So that peaks after, let's say, 2 weeks or so. And in the case of two colliding neutron stars, we also know now there's something similar, much fainter, much rarer, called a kilonova that we can also observe later on. Yeah, and those explosions also have still very high velocities, but not ultra-relativistic. And just to have an idea about the physical scales of where all these processes are happening, here is a comparison between the where the things happen and our solar system. So the internal shocks that produce the gamma radiation, they would be like our planetary system, and the shocks with the circumstellar, whatever you call it, or the interstellar medium, would be about at the position of the Oort cloud. So that's a bit to get the idea of where the stuff is. And so there's one interesting thing is that we observe these things very close in time. So you observe a gamma ray burst, and then and on one of our dedicated satellites, there's actually an X-ray and a UV telescope that scans through immediately, and they can detect an afterglow. The X-ray afterglow is usually detected almost simultaneously, and also if it's bright enough in UV, you detect it simultaneously, almost at the same time. But in reality, the processes don't happen that close in time. So you have the collapse of the system to produce your GRB. The internal shocks that create the gamma radiation are created within minutes. They are, as we said, they are in the range of a solar system, Earth, Mars, whatever, that kind of distance. And then the actual afterglow would actually be produced in the observer frame, in the rest frame within months. And yeah, the proper emission in seconds, and the observed in seconds, but the afterglow is observed within minutes. And that's because the jet is pointing towards us. That's why you get something that's similar to superluminal motion, while in reality, these things actually happen over a much longer time scale. And that's different for the supernova or kilonova because that stuff is not highly relativistic anymore. And that happens in weeks, and it's actually observed in weeks after the actual event. Okay, so just a quick recap of the two types of gamma ray bursts I've been speaking about. So we have the long soft gamma ray bursts with, so we make like a sort of artificial dividing line, as you can see up here in this plot, of 2 seconds, where 90% of the emission is recorded. Then we call it a long gamma ray burst. It's associated to a broad line 1C supernova, and it's usually found in star-forming regions and in very star-forming galaxies. And as I said, related to the collapse of a very massive star. And a short gamma ray burst is T90 of less than 2 seconds, produces a kilonova, can be in any type of host. It has really been found in any kind of, it can be star-forming host, it can be an elliptical galaxy. And it produces gravitational waves. And if they are close enough, we can actually detect them. And also another thing is why we did this dividing line. It's not just the duration of the gamma ray burst, it's also the hardness of the high energy spectrum. So short gamma ray bursts are harder in the spectrum than soft gamma ray bursts, which you see in this plot. And here is just a comparison of the luminosity of these events. So you see here a supernova is very faint compared to the peak of what a gamma ray burst can obtain. This is, I think, that was one of the brightest gamma ray bursts ever detected. The most luminous quasar is, I'd say, 6-7 magnitudes below what 10,000 times below what the most luminous quasar is that we are observing. So these things are very luminous. The problem is that they are only luminous for a very short time, because a luminous quasar is usually luminous for quite a while, and a gamma ray burst, minutes, hours, days, if you're lucky. Oh, sorry. Okay, and so I also had to started to work a bit on supernovae. As I said before, gamma ray bursts do produce also supernovae, supernova broadline, supernova 1C. They have broad lines because you have still very high velocity ejecta, because it's a very energetic explosion. And that's why the lines that you observe are broadened, because you just have material coming out at 10,000, 20,000 kilometers per second. But as you see, there is, I mean, once upon a time, there was supernova type 1 and supernova type 2. So now we have a whole zoo of things, especially yeah, both have diversified. And so originally it was like, do they show hydrogen in their spectra or not? If they don't show it, then it's a type 1. If they do show it, it's a type 2. And all of those have diversified. A 1b supernova is a supernova that does show helium. A 1c has not even helium, because probably the envelope of the star has been removed, so you only see the interior stuff. And then you have all sorts of different classes of supernovae. The things that I am studying personally most are the extremer ones of those. So of course we study broadline 1c supernovae with or without GRBs. Oh, I'm sorry. It's a problem because I'm pointing around, and at the same time the clicking goes to the next slide. And probably the most energetic ones of the type 2 supernova is type 2n. They are called N because they have actually narrow lines, but those narrow lines are interaction with dense circumstellar medium of stuff that the star probably has expelled itself in the years or centuries, millennia before it exploded. And then there's also something very interesting, a new class of supernovae that we still don't know precisely how they are produced. They're called superluminous supernovae. There's again type 1 and type 2, like in the normal supernovae. They're much more luminous than the normal supernovae. They are probably related to very massive stars, because they also occur in, at least the type 1, because they occur in very young galaxies. And the type 2 might be some sort of very energetic type 2n supernova. But that's still something that's not that clear yet. And yeah, I've been speaking about gravitational waves before, so we know that gamma ray bursts produce gravitational waves. We are actually hoping, so the next big thing in gravitational waves would be to have a very nearby supernova. Unfortunately, the detectors are still too bad to detect gravitational waves from a supernova. So you have the material is producing the black hole. That's usually not spherically symmetric. And because it's not spherically symmetric, those different distribution of mass can produce gravitational waves. The signal is much more chaotic. Then in a neutron star, it's not completely clear yet. There's a lot of models how that might look like. And of course, the signal is much weaker. So that's why you can only detect those probably within our galaxy. But of course, it would be really cool if we would detect a supernova within our galaxy. I mean, that would for the electromagnetic community, that would already be the thing of the century. Then, of course, if you take gravitational waves, you can actually really study how this collapse had been going on. And it will also send out neutrinos, and that's actually an interesting thing, because the neutrinos are the first thing that are produced in the collapse, and they get out before you observe anything else. So you might have a warning of about a day to detect neutrinos, and they say like, oh, there's something going on. The rest of the world, go and look. So that would be actually very exciting. So another multi-messenger that is already existing. So we have been detecting very high energetic neutrinos from blazars, likely blazars, because that's also not, blazars are a bit difficult to observe in electromagnetic. This is difficult to get redshift because they have a very clean spectrum. But there has been a potential detection of a high energy neutrino from a blazar and gamma radiation from these kind of objects. So, and I expect in the future to have much more of these some events that not only we observe in electromagnetic waves, but maybe also in gravitational waves and in neutrinos. I think that's the future. Okay.
Okay, and let me step into Christina's garden here and continue with the. Yes, I take care.
I cannot mute it.
I take care. Don't worry. Okay, so I'm going to speak a little bit about some of the observations and the studies that we are doing or we have been doing over the last years. Let me start with multi-wavelength observations. So as Christina already mentioned, these gamma ray bursts are created by two types of objects, the long gamma ray burst and the short gamma ray burst. But they both have in common the radiation mechanism of what we call the afterglow, when the jet collides with the interstellar medium. That process emits a synchrotron spectrum, which is what I've depicted here, from meter radio wavelengths all the way up to X-rays. And you can see that this is characterized by segments of power laws and characteristic frequencies. So by monitoring the position and the evolution of these characteristic frequencies and the slopes of this straight power laws that we have in the different regions of the spectrum, we can determine a lot of parameters of both the explosion and the medium around the burst. We can determine the acceleration processes. We can study the density and the density profile of material around the star, the geometry. We can also study microphysical parameters like the fraction of energy stored in magnetic or magnetic fields or in electrons. So there's a lot of parameters that we can study if we have good enough data. For example, here's an example of how a GRB evolves. This is from a work that our PhD student Rubén Sánchez Ramírez did in 2017. Where you can see radio wavelengths all the way to X-rays. Here's the optical and near-infrared, ultraviolet. And this includes one of the first observations with the ALMA telescope. And you can see how the shape of the spectrum evolves with time. And by studying this, we can determine all these parameters. Here is an example of a work that we are doing now, which is much more complex. You can see here on the left, you can see the light curves in different wavelengths. These are radio wave bands from meter wave bands to submillimeter. And here you have the spectral energy distribution from radio again to X-rays evolving in time. This is different frequencies and this is evolution in time. And you can see that it's much more complicated than the simple model that I put before. This is a data set where we have observations obtained by more than 20 telescopes over a time span of more than 3 years. We're still observing this event, which happened in 2017. You can see the naming is the year, the month, and the day in which that event occurred. And then we have A, B, C, D for the number of event on that day. So you can see that after 3 years, more than 3 years, we can still observe this event in the very long wavelength bands. In optical, it disappears very rapidly. So this is much more complex modeling. We have a special interest in the millimeter and sub-millimeter range, because that's where we find the peak of the synchrotron spectrum over the first days after the explosion. And that allows us to do some additional science. It has the advantage that it has no absorption effect. So if we have a burst that's happening in a very dense region of a galaxy where there's a lot of obscuring material, it doesn't affect these frequencies. Whereas in optical or in X-ray bands, we have a significant absorption. We don't have scintillation, which is a problem that we have in centimeter, decimeter bands, where the medium between us and the object makes the light curve fluctuate dependently on that medium, but independently on the actual source. So that it makes modeling much more complicated. We can observe molecules at all redshifts. And we also, that reverse shock of which that Christina mentioned at the beginning is often seen in that regime. We are having programs for this kind of follow-up at the ALMA observatory that you've probably heard of in the Atacama Desert in Chile at 5,000 meters. And we also use the NOEMA array, which is in the Alps in France. In 2012, we made the most detailed sample of millimeter and submillimeter observations. We basically gathered all the observations that have been gathered until the start of operations of ALMA, and we did the first luminosity functions of gamma ray bursts at those frequencies. Actually, this was the first ever paper of that ALMA observatory, because during the commissioning of the observatory, we managed to get some data of one of the events, the one I showed before, and this was the first of, I don't know, more than 1,000 papers that they have now. I now move on to the radioactive ejecta of gamma ray burst. As Christina mentioned, there are two types of events, and those two types of events produce either a hypernova or a bright supernova. They like to call it also hypernova, but it's a broad line 1C supernova. So you can see here the evolution of such an event. This is a data set that we're working on, and that's probably one of the most details until now. And you can see how those features in the spectrum are very broad and evolve in time. Those are the ones that appear in long gamma ray bursts. So in the collapse of a very massive star that collapses into a black hole, producing that GRB. On the other hand, there's the short GRBs, which are the merger of two neutron stars that produce an R process kilonova. That's where a significant part of the very heavy elements of the universe are formed in this kind of explosions. So let me show you how we observe these things. So as we said, this is a light curve of a gamma ray burst, where you can see at the beginning, during the first 2 weeks, this is in logarithmic scale, you see that the light curve is dominated by this power law decay. This is produced by the afterglow. The afterglow is normally extremely bright. Whoops, sorry. And you can see that after the second week or so, there is this bump appearing in the light curve. This is the supernova component. So you can see that during the first week, it's very difficult to see anything of the supernova because of the brightness of this afterglow. Later on, the supernova dims out until the galaxy in which it happens dominates. So you can see that both the supernova and the afterglow are brighter than the galaxy in which they happen. But the afterglow is just extremely bright. So this is a case in which this did not happen like this. It was a low luminosity gamma ray burst. So the afterglow was actually very faint. It did not dominate for 2 weeks, but it dominated only for the first hours. So we saw in the light curve that there was this bump emerging, and this bump did not have a synchrotron spectrum, but had a thermal spectrum, similar to what a supernova has. When we took spectroscopy of this event, we saw something that had never been observed before in a supernova, and it's very, very broad absorption features, and that were moving, expanding from the explosion at a velocity of 100,000 kilometers per second. This is the highest speed that has ever been detected in a supernova. And this was just 1 day after the explosion. We believe that this is produced probably in all events, but we never get to observe this because there is the afterglow appearing and dominating during that time. In this picture, you can see how we interpret this event. We have this star exploding, we have the jets being produced, and we have these yellow things here that are the cocoon, or we call the cocoon. It's like material that has been dragged from the core of the star and expelled outside the star at very high speeds. And indeed, if we looked at the material of this, at the composition of this material that's expelled here, it has a composition that is dominated by iron and nickel in a way that you don't expect from the outer parts of the star. So we're getting material dragged from the very center of the star, which is something that had been predicted but never observed before. So this was a paper that our postdoc Luca Izzo led in Nature in 2019. This is a very, very famous event that many of you have heard about, and is the first gravitational wave for which there was an electromagnetic counterpart. This was a short gamma ray burst, very, very nearby. It's by far the closest short gamma ray burst ever detected at only 40 megaparsec. That is a little more than 100 million light years. It was very bright, not very luminous, but it was very bright because it was very close. So the luminosity of it was not that enormous, and it had the peculiarity, if you compare here several light curves of supernova, that it was extremely fast. So it reached the peak and decayed very, very fast. It also evolved from blue to red very rapidly. You can see here the light curves, and this is probably the best observed event in history of GRBs for sure, but of many objects in the history of astronomy. For 2 months, there was basically all observatories in the world trying to observe this thing. Although it was kept secret because of the agreements that we had with the gravitational wave programs. This is the spectroscopy of that kilonova that was observed, and you can see the evolution of this, that it evolved very fast from blue to red. And there's some features here that are not completely explained yet, but that seem to be due to very heavy elements that are being produced by these R processes. Okay, and here I'm gonna hand over to Cristina again. So let me unmute her, and I'll mute myself so she can take over.
Okay. So we continue a bit with with gamma ray bursts, but going to the also events that are very peculiar in itself. Because before we heard one where we observed something that we should observe everywhere, but due to the afterglow outshining, we don't usually do. And this was a very interesting event that happened already 11 years ago on Christmas 2010. That's why you also call it the Christmas burst. I would call it my birthday burst, by the way. It was a very peculiar event. It was very long. One of these things that are not just a few seconds or minutes, it was actually more than 2,000 seconds. We don't know exactly how much because there has been a gap in the data. At a sort of moderate redshift, which we thought originally that it was at redshift 0.3, but it turned out to be at redshift 0.8 because we finally got emission lines from the very faint galaxy. And so the surprising thing in this event is that at no time we had a synchrotron afterglow. We only had an evolving black body emission. And that was very, very, very strange. And so in the end, there was also some very faint supernova detected. It's actually very difficult to detect these supernova at redshift 0.8, so it's not very surprising. But the supernova itself was also very peculiar. It was probably very blue, but as I say, it's so high redshift that it's very difficult to model. But so that was a very, very special event. So we had been thinking about what the hell can produce something, or what makes the synchrotron emission be suddenly a cooling black body. And so together with some theorists, we developed a model that had actually also been thought a bit before, but there has nothing ever like that had been observed. So our model was that we have, I hope if you click on this, it's going to work, that we have a sort of merger between, or sort of, we have a merger between an evolved helium star and a neutron star. And in the process of this merger, maybe not very long before the final merger, some shell, probably a very thick shell, you can imagine it like a very thick donut, was ejected before, which was still not very far out of the system. And so in the final merger, we produce something like a gamma ray burst, but then the jet cannot get out freely of this system. And because of this very strong interaction with the already existing circumstellar material, we basically thermalize the jet. So that's why we get some sort of cooling black body emission. The black body, of course, would not be like a spherical symmetrical black body because you have a like an emitting surface on top of this funnel coming out of this of the rotation axis of this donut. But you basically don't have any synchrotron emission left. It's all thermalized. And that's why you get this interesting thing that we observed. We actually could also determine that there was two black bodies. There was one black body further in that we saw in the X-rays and one further out at about the distance of, let's say, Neptune or so. And so that unfortunately hasn't been observed before and unfortunately not ever since. So that seems to have been a very special event. So we are waiting for the next Christmas burst. And so now we switched to something completely different. I said this is about peculiar events. That was, well, there's a historical background why we got interested in all this and why I now started to get into supernovae, which is related to the galaxy that this was in. So there was this interesting event in 2015, which was not a gamma ray burst, nothing to do. But we knew the galaxy that it occurred in, NGC 2770, at a distance of about 30 megaparsecs, so very close to us. And the galaxy has been known to us before because of reasons of a gamma ray burst, or not gamma ray burst. Actually, it turned out to be just X-ray emission from a shock breakout of a very luminous supernova. And so we got some alert at some point that something might be going on in that supernova and that galaxy. The galaxy actually had hosted 3 supernovae within 10 years. And there seemed to be something more going on, so we started to monitor it. And there was actually then first, it was very strange. There was like some outbreak in the year before, and then suddenly in spring it started to rise, then it started to fall again, and suddenly it exploded in mid-May 2015. And then we followed up this event because it was very peculiar. It turned out to be a type 2N supernova, so because we detected these narrow emission lines. The progenitor was likely to be a more than 50 solar mass star, possibly a luminous blue variable. The most famous luminous blue variable in our galaxy is Eta Carinae, which is much more extreme than this event was, but maybe it was something similar. And yes, another slide. And so the very interesting thing was that we serendipitously have spectra of this object before it exploded. As I said, we had been studying the galaxies for other reasons. So we actually obtained a sort of IFU data cube, not with an IFU instrument, but just by observing things in different slits and shifting the slit. And the position of this object, meaning the star, was actually in one of these data cubes. So we have a spectrum of the object from 2013 at the onset of one of its outbreaks. So I didn't mention that before in this slide. Can I go back? So we observed this object. We went to the archives. We actually even had people getting magnetic bands getting digitalized somewhere in the UK. Because it's such a nearby galaxy, it had been monitored every now and then. And we found out that this object had outbreaks of about 2 magnitudes over at least 21 years. That's how far back we could go with the data to have enough quality to determine that. And so at the onset of one of these outbursts, just before we got this serendipitous spectrum that you see down here, and then we could model with an LBV. And so this was possibly the first spectrum of a star that went supernova before it exploded since the famous supernova 1987A, where we know the progenitor star. And there is still some remnant here. So at the moment, we are not sure whether the star really exploded or not. So I proposed this very crazy theory, maybe, that because there's one thing we still don't know how Wolf-Rayet stars are made. Wolf-Rayet stars are possibly the progenitors of gamma ray bursts. And they are stars which are basically just the hot core of the star left. They have ejected of most of the hydrogen and helium. And only the inner parts you still see, but no one knows how to produce these stars that are on the left side of the main sequence in the Hertzsprung-Russell diagram. And so I proposed the theory maybe such an event would be a way to like shed the outer parts of a star and make it a Wolf-Rayet star. So that's, you have to see what's going on with that object. Maybe it also just exploded, and that's the the supernova random basically already. So that's a future project that I'm working on. I want to get more of these pre-explosion spectra because I think it's very interesting that we know what kind of stars actually explode in which type of supernova. I think there's a lot of surprises that we can get there. So at the moment, I have a big project going on. Hopefully, it depends on how much time I have and how much funding I'll have in the next years to target all galaxies that have had already all star-forming galaxies, less than 30 megaparsecs, that have already had several supernova in the past, so that makes it more likely that there might be another supernova, which means there's a lot of star formation going on. The idea is to observe that either with big IFUs like MUSE, or with a technique that we have already used for NDC 2770 drift-can spectroscopy, where we have already one galaxy observed with OSIRIS, the famous fireworks galaxy 6946, which had 9 or 10 supernovae. And we are aiming for some more. And yeah, we already have some results from some data cube that we found in the MUSE archive of M100, and that we actually have 2 candidate pre-explosion spectra. One of them might be a cluster. It seems it's a bit too bright. You see here in the Hertzsprung-Russell diagram, our candidate appears in a region that it shouldn't be. This is probably a small cluster, either a cluster or a system of several stars superimposed in one spaxel. And another supernova 2019 EHK, the spectra have actually been taken 2 days before the official discovery of the supernova. So that might be the earliest ever spectra of a supernova. There's not too much to see, but I think it's very interesting. That hasn't happened before. That's, again, I mean, serendipitousness sometimes gives you very exciting things. Okay, and I'm just going to show you a little bit of the other things that I'm doing related to gamma ray bursts and supernovae. You can not only study the event and their progenitors from the actual event, or as you saw before, from trying to get spectra or information of the object before it exploded. In many cases, you cannot do that. For gamma ray bursts, we'll probably never be able to do that because usually, at least the long gamma ray bursts are very far away. You'll never be able to, or never, not in very short, not in our lifetime, be able to pinpoint a star at a redshift of not even 0.2 or something. It's just impossible. And 0.2 is still no redshift for a gamma ray burst. It's still very close. So what we do is we study the environment, either the host or the environment of the gamma ray burst, and try to get information from that. Sorry, I just have to quickly connect my computer, otherwise I'm going to be shut off. And so, as I said before, long gamma ray bursts are usually in highly star-forming galaxies. You see that up here. Here you see star formation rate or specific star formation rate of normal field galaxies, and gamma ray burst galaxies are up here, long gamma ray burst galaxies. They're also usually more metal poor. And short gamma ray burst hosts are much more diverse. They usually have a bit higher masses than long gamma ray burst hosts, and they can be any kind of metallicity, for example. And yeah, I said that before. You can, if you're lucky, you can observe an object before it explodes. They have been doing that a lot for supernovae, not doing spectra, but going back to the Hubble archive. At least they have several bands. You can sort of model the black body, and then you can put it in the Hertzsprung-Russell diagram, and you have stellar evolution tracks, and then you can say, okay, this thing had a mass of whatever, 30 solar masses, 15 solar masses, and it was probably this and that type of star that exploded. You can usually not do that for gamma ray bursts. That's why I have to do indirect methods. And here you have some small comparison of the size of gamma ray burst hosts. These are usually not very big, except for one exception, which is this one here. This is actually very new. That's a gamma ray burst from 2019, which is a galaxy about the size of the Milky Way. But most gamma ray burst hosts are long gamma ray burst hosts are small dwarf galaxies, which makes studying the environment even more challenging because it's often very difficult to resolve these objects because they are so small. And these are just some examples of what I've been doing both for supernova that I've been quickly mentioning in the beginning, that might be very massive stars that live very shortly. So we actually had that object here, PDF 12 DAM, that was in a galaxy that it is very, very young with very extreme emission lines, as you see. As you see a lot of, you see these traditional emission lines of H alpha, O3, H beta, and oxygen 2. And then you zoom in and you start to see many more lines. You see all the entire Balmer series down to when it disappears. And a lot of other lines that we don't often see, usually don't see in gamma ray burst hosts because those hosts are not that extreme. And so, for example, 50% of superluminous supernova type 1 hosts are extreme emission line galaxies, which are basically, maybe heard of green pea galaxies, but they are these extreme galaxies at a certain redshift. That's why they appear green. But at any redshift, they're called extreme emission line galaxies because they are very young. They have host very young solar populations. And so we think in this case, it was a confirmation that it was a very massive star that exploded there, possibly even more massive than what we see for gamma ray bursts. And the other one is just an example that sometimes we have to be careful in interpreting things. We really have to study the stellar population. That was an object that also called some kind of attention because all superluminous supernova type 1 should occur in metal poor galaxies or metal poor stellar populations. And then we had a large spiral galaxy that apparently had solar or maybe even super solar metallicity. It's like, this is against our models, so how can we get an agreement with that? And we actually started to model the stellar population at the site of superluminous supernova. And for now, there are actually two populations. There's the dominant one that you see that is old or older. But there is also one metal poor, very young stellar population that maybe was created in the interaction because that one actually has a companion galaxy. And you actually see, if you look closer, you see that the galaxy is not symmetric. It's not an I spiral. It's somehow distorted. So there seem to have been some interaction going on, and that possibly created a new starburst that was then responsible for the superluminous supernova. So the metal-rich thing was not a problem. It's because you haven't looked deep enough. So that you have to be careful with interpreting. And you can do the same for gamma ray bursts. Usually the things are less resolved. But in some cases we are lucky. The famous one they have been mentioning several times, GRB 171205. So that's like, you see, it's our it's our big thing. We have the Nature paper on the cocoon. We are studying the afterglow. We have supernova spectra of almost a year, and we have very nice data of the galaxy with MUSE. We have HST, very high resolution imaging. We even have data from ALMA. Very high resolution, which I haven't shown here, but we have CO data where we see nicely these spiral arms, the inner spiral arms of the galaxy. There's unfortunately not much emission at the GRB side. But also here we have been studying all kinds of aspects of this galaxy. As you see here, for example, the stellar population at the GRB side is again very young. It's in the outskirts of the spiral galaxies. Usually in spiral galaxies, we have sort of what we call inside-out formation scenario. So we have the star formation usually goes from the inside to the outside. So the outskirts are usually younger and also usually more metal poor than the center. So it's not surprising that we see a gamma ray burst which possibly needs a low metallicity in the outskirts of a spiral galaxy. And yeah, that was one of another very interesting gamma ray burst that we were not sure whether it was a long or a short gamma ray burst. Gamma ray burst 60505 was also in a spiral galaxy, actually a dwarf spiral galaxy. That's actually, although it's a spiral, not all spiral galaxies are like the Milky Way or Andromeda. There's some that are actually pretty small. And so we were not sure whether this was long or short because the duration was about 4 seconds. So I studied the galaxy, and the environment looked very much like a long gamma ray burst environment. Metal poor, very heavily star forming, although maybe not the most exceptional region in the galaxy, but everything pointed to this also actually being coming from the collapse of a massive star and not a merger. So despite being on the short end of the long gamma ray burst distribution, from the environment, you could determine that it was very likely a long gamma ray burst. And then you can also do things of like how to determine whether the star formation is actually coming from, or if it has any effect on the galaxy. So they have been studying a sample of gamma ray burst hosts with high spectral resolution. And we actually have been seeing in most of them, and some of the data are maybe on the edge of just being good enough, that we see some additional, so you have these all your narrow absorption emission lines, which is the normal warm ISM in your galaxy. And you have some broad underlying component, which we think comes from, either it's stellar winds or possibly combined supernova explosions. You see these very nice in there, they're called cigar galaxies, where you see these outflows, these plumes coming out of the galaxy. That this is maybe something that like this would look like if you could look at it closer. And you can actually also see this material coming out of the galaxy that's ejected by either by stellar winds or by supernova explosions. So you have the shells blowing out and sometimes getting as enriching the intergalactic medium with that. You can also observe that in absorption. And yeah, last very interesting thing that I'm working on right now. This is the first gamma ray burst that we have detected very high energy emission, which possibly cannot be produced only by the gamma ray burst in the jet. So you need something that basically upscatters your gamma ray photons to even higher energies. And the first one that we detected was GRB 190114C. By now we have 5 or possibly 6 detections at very high energies. So the thing is always once you detect one, you usually detect more. Unfortunately, it didn't work with gravitational waves, but we hope. And so what can be causing those upscattering of the photons that we can observe them at very high energies that are not consistent with the extrapolation of the spectrum from lower energies? And we think we have a very strong hint in the optical spectra of that gamma ray burst. We have observed lines, very highly excited states of titanium and iron that we have not observed in any other gamma ray burst. And the titanium lines, I'm basically sure we have not observed them ever in any other astrophysical source. And so that's probably levels that have to be excited by the UV radiation of the gamma ray burst, but you need a very dense medium because otherwise you would not observe them. So we think that is a hint on what explains this very high energy radiation, is that you need a very dense medium. In that case, it seems likely because that was actually a gamma ray burst that was detected close to the center of its galaxy, which is very exceptional. Although there's another case of this giant galaxy that I showed you before, 1908-29, the Milky Way sized GRB host. There we also have very high energy detection, but the gamma ray burst is in the outskirts, in one of the spiral arms. So that is something that we need to study further. And we also have indication that it's a very dense medium because we detected something called diffuse interstellar bands, which is molecules that are only usually found in very dusty environments, and that we also have never seen in gamma ray burst. And with that, I hand over again.
Okay, and I take over for the last part of the talk. I'll try to be quick because we're going a little bit long. Okay, so I'm going to continue speaking a little bit of what Christina has been saying about all this. She's been talking about absorption, is the use of gamma ray burst as lighthouses. So we said these are extremely bright objects that can be used, that have a very simple spectrum. That's also an advantage. Is this power law spectra of the synchrotron imply that if we need to model that, we just in an optical infrared spectrum, we're just going to have a power law, and everything that we see happening to that power law, any deviation from the power law, any absorption features that we see there are going to be from the media that are between the gamma ray burst and us. So that's very interesting to study study the intervening medium. And here you have an example of how this works. Here you have it explained with a quasar, but a gamma ray burst is similar, only that the spectrum is much simpler than a quasar. So where you have what we call the metal absorptions from the host galaxy, but also from any other galaxy that you can find in the medium between that galaxy and us. You can see here that the distribution of redshifts, or here also of distances, that those distances or ages of the universe, that's the look back time in the universe. You can see that the average of gamma ray bursts, they are around redshift of 2. That's more or less when the universe was 20% of its age now. But we can go all the way down to the era of reionization. So there are very interesting objects that can help us observe all the universe from the very first stars to our days. And by observing these features, these lines that are in the line of sight, we can determine composition. We can determine velocities of that material. We can study the evolution of star formation across the universe. So we have been, as Cristina said, leading proposals here in Spain at the Gran Telescopio Canarias, which is the largest optical telescope in the world, and also with collaborations at the ESO, at Paranal Observatory in Chile, to gather as much spectroscopic observations as we can, because they are extremely valuable for these purposes. So in order to manage that data and other data from other observatories, we've created a public database of gamma ray burst spectroscopy, which is nowadays the largest in the world. And for that, we got a funding from the Marie Curie Career Integration Grant and the Becas Leonardo from the Bebia Foundation. And this basically collects data from all observatories. We have data from 18 different spectrographs and more than 800 spectra from 270, more than 270 GRBs nowadays, although this is continuously growing. We have also created tools for the analysis of these large samples. So here are some diagrams that we created to compare the absorption features of a gamma ray burst with the average that we see in a normal burst. The normal would be the black line, and the red would be the ones of a particular event. You can see this one would be very strong lines, this one would be very weak, and then you can also, by these diagrams, understand in very rapidly the peculiar composition or ionization ratios that an event can have. So that allows you to do further studies. Here is an example of what a good gamma ray burst spectrum looks like. Here we have the Lyman forest and many absorption features. Yeah, too good spectrum. Cristina had to do the line fitting for this. It had 9 or 10 different absorption components with hundreds of lines. So that took a lot of work. That's a paper that we published in 2019. And from this, you can extract a lot of information. So this light had gone not only through the different clouds in the host galaxy where it happened, but also through another 8 or 9 galaxies in the way to Earth. From this information, we can determine the metallicities, which is quite cool because you can determine the metallicities directly by measuring hydrogen and some other absorption lines. So you can get the radio, that's the real metallicity. And when the thing fades down, you can also study the host galaxy in emission. So you can get emission line and absorption line metallicities, which is something that you cannot do with other objects. We can study the dust and metal evolution. You can look for molecules. So we're doing a lot of cool stuff with all this data that we've gathered. Another thing that you can see is that if you have resolved spectra resolved in time, you can see that some of these lines are varying. The lines that are very close or relatively close to the burst can be affected by the UV radiation of the burst. This means that some lines will get excited and de-excited with time. So if you progressively observe them and knowing the amount of radiation that you have, you can even determine the distance at which those clouds are. One example is the 1901 14C that Christina was mentioning before, that has excited lines of titanium that have never been observed before, and that we're still trying to model because we have never done that before precisely, and that is probably material not very far from the GRB. Although when we said not very far, we're talking about probably hundreds of light years from the event. Christina also led a paper where for the first time we observed a varying not just metallic lines but also Lyman alpha. So this was a cloud of hydrogen that was very close to the GRB, closer than other things had been observed before. Here you have a graph where you see different GRBs where we have measured the distance of those clouds to the actual event. As for the short gamma ray burst, as Christina said, they are found in much more varied types of galaxies as we do find the long gamma ray burst. Long gamma ray bursts are star-forming galaxies. They are stars that last only a few million years. So they can only be happening in star-forming galaxies, whereas short gamma ray bursts are the merger of two neutron stars. In order to get two neutron stars, you need to have had two massive stars first that evolved, exploded a supernova and created a neutron star. The other one exploded as a supernova and created a neutron star, and then by emission of gravitational waves, they in spiral and they form this merger, which emits the short gamma ray burst and the gravitational waves. So those can happen in many different kinds of galaxies, like from elliptical galaxies, some spiral galaxies, and even in some cases you don't find a galaxy because the object has been expelled from the galaxy. Here I'm going to give you two examples. This is 130603b. This is a short GRB that I studied in 2013. This was the one for which we got the first spectroscopy of a neutron star merger. It happened in the arm of a spiral galaxy, which favors, as it's still in a relatively star-forming galaxy, it favors a process in which the merger has happened rapidly. So maybe hundreds of millions of years and not several giga years. And on this burst, there was also the discovery of the first kilonova before the gravitational wave hype came along. And for that, we contributed with observations from GDC. And here, that's the distribution of where you find short GRBs in late type, so not very star-forming galaxies are the majority. Early type, those are galaxies with a lot of star formation. There's a 17% that don't have a host galaxy, and some others that we don't have enough data. The second example is a paper that's being led by our PhD student that is the first short gamma ray burst spectra. This is a very good spectra, and it happens to be at a restive of 1.7. This means that the hydrogen line, which is far in the UV, is redshifted all the way into the optical. So we can determine those metallicities that I was talking about before. In the previous one, we could not do it because it was too close and we didn't have UV observations. So in this, we could do a very detailed analysis of the composition of that environment. And it's a very thin environment. It's very weak lines. It's lucky that we got a very good observation with a very large telescope in Chile, and we reacted very, very fast. So this is one of these events where when the object faded out, there's no galaxy below. So there must be some material because we see some absorptions, but they are very faint. There's basically no dust. This is a dust depletion diagram where you see how the dust affects, and there's very little dust, and the metallicity is very, very low. So this is a completely different environment to the other one. So these events can happen in many different ways. So there's still a lot to be learned from there. And I'm going to finish the talk just mentioning a couple of technological projects in which we're involved. All this transient astronomy requires very specialized instrumentation. We have been involved in instrumentation from the beginning. Christina was involved in a multi-channel camera called GROND during her PhD. I was involved in the X-shooter spectrograph that's at the very large telescope in Chile during my PhD also. And we have been also decided to lead our own instrumentation. And we actually proposed in 2014 an instrument that we call OctoCam for the Gemini telescope, which was at the time looking for an instrument. This is an instrument in which I was the principal investigator and Cristina did the project manager duties. It's an instrument that can observe simultaneously in 8 bands, optical and infrared, and observe a field of view of 3 by 3 arc minutes. It can do spectroscopy in the complete optical and infrared range at a quite reasonable resolution. It can get very high resolution, a very high time resolution, so we can study the variation of that emission with time, and it's very easy to calibrate. It's a very efficient instrument. So in 2014, we proposed it. We got funded a feasibility study. That's missing a Y there. And well, after that study, there was an actual call for full funding of the instrument, which we won. And the instrument was funded with $15 million by the National Science Foundation of the US. And well, this project implied that we injected also 1.5 million euros into the Spanish industry. And well, we are working on that project until 2017 during the conceptual and the preliminary design. We are now proposing a similar instrument to be built at the GDC. So there will be Octocam in the southern hemisphere and GATOS in the northern hemisphere. It's a very similar instrument, but with some other capabilities that Octocam does not have. So apart from the 8-band imaging and spectroscopy, we can do integral field spectroscopy, both with adaptive optics or without adaptive optics. And we can also do spectropolarimetry, which is also a very interesting technique that can allow us to understand better geometry and magnetic fields. So I'm going to stop here because I think we've gone pretty long, and I think we can take some questions if you want to ask anything. So, Casco, thank you very much.
Thank you very much, Antonio and Cristina. So as you have suggested, so now time is open for questions or comments. Please raise your hand or send the questions to the chat, whatever you prefer. So any questions? I mean, if yeah. Yes, go ahead, Jonas.
Okay, can you hear me?
Yes.
Yes,
Yeah.
we hear you.
So yeah, I have a question about these events with no host, because I think that's really interesting. So my question is, given the distance to the closest galaxy that you can estimate from these events and the typical velocity of a kick out of this pair of neutron stars from the galaxy, is there a possibility that this is really an object that has been expelled from a galaxy, or maybe it's just a very faint galaxy that you are not able to detect?
Okay, I take that one. So there are the two things, actually. We expect that during the explosion of those supernovae that have to make are required to make the system, the system can be expelled. They get a kick, what we call a natal kick, that can accelerate that to hundreds of kilometers per second and actually expel that object from the galaxy. In the case of what we showed before, 160410A, there is still a little bit of material on the way. So that's peculiar because we see no galaxy when we look, and we have pretty deep observations, but we still see a little bit of material. So there can be both. I mean, we know that some have no galaxy whatsoever. In this case, we do see a bit of material in the line of sight. So there is some material, but so it's not completely isolated. So maybe it's expelled, but there's some material going also with it. There's some cases also where we try to get spectroscopy and there's basically nothing there, no lines. You just get the synchrotron spectrum, and in those cases, yes, in those cases there's basically no host galaxy. So it's something that's been expelled from there, and you see no material.
Okay, thank you a lot.
Thank you.
More questions? So, okay, in the meantime, let me make one myself, even if I'm not an expert at all in the field. So, but I was curious because you mentioned mostly at the beginning of the talk the links also to the gravitational waves. So, let's say in a very general context. So, do you think that let's say the arrival of the let's say, observations through gravitational waves will influence a lot also the activity in gamma ray burst? Do you think it will not have any influence at all? Or how do you see the connection, let's say, between these two fields?
So, I mean, we have had only, unfortunately, one event so far in 2017. Since then, there has been a huge or several huge collaborations being established, because back then it was very chaotic. There's actually a lot of duplicated observations, which of course we want to avoid. And so there are several major collaborations, some of which we are also involved. There's the engraved collaboration at VLT to take spectroscopy. As you saw in one of these slides, there's this spectroscopy of kilonova. They are not aiming at detecting a counterpart, but once there's a counterpart, to follow up the kilonova. And that's so the last event was like the first one where there was actually a series of these kilonova spectra. And as Antonio mentioned, there's still a lot to learn because there might be lines. We still want to understand what kind of material is produced in those explosions. How do they influence the chemical evolution of the universe? There is possibly, I mean, if you observe 3-4 more events, they're probably all going to be different. So there's a lot to learn from that. So there's a collaboration just mainly focusing on that, on spectroscopy follow-up from VLT. We are involved in another collaboration that's actually trying to detect the counterparts, which is also unfortunately not easy. That's a big problem in gravitational waves, that the error boxes are still very large, because a gravitational wave detector in itself has very little directional information. It knows there was a gravitational waves, but there's very little information where it came from. I mean, there's some angles where it cannot detect much, so from there you can say it didn't come from there. But if you want to get a position, you need to do triangulation, so you need several gravitational wave detectors. They are extending now, so in the last runs there has only been 3, the 2 in the US and Virgo in Italy. And they have now commissioned also one in Japan, in the Kagra mine, where it's also the Kamioka mine. It's called Kagra. It's the mine where there's also the big neutrino detector, Super Kamiokande. And they are working on because they all need to ramp up in sensitivity in order to be sort of useful for the common detection. And they're planning one in India. So once we have 5 detectors, start to be able to narrow it down to something that you can observe in reasonable time. The thing is, these error boxes are enormous, and even the largest field of view telescopes can only observe a tiny bit of it. In the case of 1708-17, we were very lucky that it was very close, and they actually found it not by observing all the error box, but they're actually targeting possible host galaxies. And they had because it was so close, it was like 50 or so that they started to monitor, and then they very quickly had a counterpart. So there's a lot of practical improvements to be done in that, but I think there is a lot to be learned, especially once we try to have smaller error boxes. We have higher sensitivity, although that might also be difficult because these things go further out. But then, of course, at some point we can just study possible redshift evolution or whatever it might be. But I think there's a lot of work to be done. But it's really hard work if you get down to the everyday thing. And then, of course, at some point we hope to maybe detect gravitational waves from other sources. I mean, most of the gravitational waves detected are actually not neutron star mergers. There have only been a few. I mean, the famous one, and then in the last run, there have been a few candidates. None of which we have found any counterpart, unfortunately. But most of the gravitational waves detected are mergers of black holes. And unfortunately, those objects seem to have basically no material left in their surroundings. So there's no actual explosion. So you only see the gravitational waves. That's a pity. But maybe there's intermediate things like a black hole in a neutron star, and you might see something. So I think there's a lot to be done, and a lot of discoveries to be done. And of course, I'm hoping for the big supernova plus neutrinos plus gravitational waves.
Okay, any further question? So I don't see any. I think probably it's time for lunch for all of us. So let me again, Antonio, Cristina, thank you very much for this very nice talk, very nice overview of your work. And so let's say keep in touch and see you soon, I hope.
Thank you very
Okay.
much for having us. It's
Okay.
it's been very interesting and yeah, thank you.
Okay. So
Yeah,
see
thank you very much.
Bye.
See you around.
Bye bye.
Bye.
See you around.